the advantages and There are many everyday uses for electricity in the home. It's very important to understand electricity and be able to use it safely. That's what this film is about. Different electrical devices have different power ratings. They use more or less electricity according to their power and take greater or smaller electric currents when they're in use. Let's look at 3 very common domestic items. We'll start with an ordinary electric light bulb, a 60-watt bulb. It takes very little current indeed. Switch it off and on again. The amount of electrical energy being used is measured by an electricity meter, a joule meter. The greater the consumption, the more quickly the disc rotates and the counters change. A colour television set. This has a greater power rating. It takes a big surge of current when it's first switched on, then settles to a smaller value. The disc of the joule meter rotates rather faster than it did with the 60-watt bulb. An electric fire. This one has 2 1,000-watt heating elements, so its power rating is much higher than the bulb or the television set. 1 bar on. Now let's switch on the other element. You can see that the fire now takes a current of over 8 amps, much higher than for the other appliances. Using an electric fire means using a lot of electricity. Watch the disc on the meter and see how it speeds up when we switch on the second bar of the fire, doubling the power. Now for another demonstration. Any electrical appliance will use up more electricity if it has to do more work. Producing any kind of energy means using up some other kind. This electric drill turns electrical energy into mechanical energy, the rotation of the drill bit. When it's simply turning in air, it takes a quite small current to run the motor. But as soon as we start drilling into a block of metal, this is harder work for the motor and its power consumption increases. Watch the needle of the ammeter. When a wire carries a current, it heats up. For a given metal, the thicker the wire, the smaller its electrical resistance. So a given current heats it less. We're going to pass a constant current around this loop, which has thick wire at the top and thin at the bottom. Watch what happens. The thinner wire got so hot that it melted and broke. It couldn't carry that particular current. Another demonstration, and we'll need the correct type of fire extinguisher handy for this one. The greater the current to be carried, the thicker the cable must be. This 2,000-watt electric fire takes a high current, as we saw. Let's look at what happens if we connect it to the mains with thin lighting flex, which isn't intended to carry such a big current. The wire inside the insulation is thin, and its resistance will cause it to heat up as the current flows. After a quite short time, watch what happens. The 2 1,000-watt heating elements are taking a big current, too big for this flex. Imagine this happening in your home, maybe with no one in the room. Time to use that extinguisher. Many fires are started by faulty wiring, especially by using cables that won't carry the current taken by appliances like fires and kettles and so on. Sooner or later, the wire gets so hot that the insulation melts and a fire is started. At the Greater Manchester County Fire Service headquarters, the safety officer talks about one such tragedy.
This piece of wiring was taken from a house in which 2 children died in a fire. The fire was started because of faulty wiring, and the original source of the ignition was in fact destroyed. When we went through the building, we found that wiring typical of this went right through the house. The occupier had made taped joints and fastened together different thicknesses of wire. He had not used a proper junction box, and he had not obeyed the golden rule, which is if you are going to wire anything, call in the experts.
We make use of the fact that a wire will melt if it carries too high a current in fuses. This 60-watt bulb takes only a small current, so we use a quite thin fuse wire. If anything goes wrong, say a short circuit, which means that a much greater current flows, the fuse will blow. But otherwise it stays intact. In many modern fuses, of course, the fuse wire's hidden inside a little cartridge, and you can't see it. That fuse will only carry a current of 3 amperes or so. If we put it in circuit with an electric fire, which takes a much bigger current, the bigger current will cause the fuse wire to melt and cut off the supply to the fire. So, for a circuit supplying higher power appliances, we use thicker fuse wire, which will carry the higher current. But you only use such a fuse when there are things like fires and kettles to be connected up. The resistance is low because the wire's thick and it doesn't reach melting point. But using the correct fuses won't help you if you make other connections wrongly. We're going to wire up an electric fire, deliberately, very carelessly. Like our other demonstrations, this isn't one for you to try for yourself. Did you notice that straggly bit of wire sticking out? When we connect this, the live wire, to the junction box, that strand's left touching the body of the fire. And the earth lead, green here, as on some older cable, but it's green and yellow on modern cable, hasn't been connected to the earth connection on the fire. We'll put the fire together again. Really, of course, an appliance like this should only be wired up by an expert electrician. The fire works perfectly well. What you can't tell by just looking is that all the metal work is live because of that stray bit of live wire touching it. Watch. You'd get a severe electrical shock and perhaps a terrible burn if you touched any part of the fire. Now suppose there was still that frayed lead touching the metal casing, but that the earth lead had been connected up. Remember, the earth lead's green and yellow on modern wiring, but there's still a lot in use with just this green insulation. Like all connections, the earth lead must be tightly held in place. Now, when we switch on, a large current will pass to earth from the live casing, enough to blow the fuse. There'll now be no electrical supply to the fire, and it will be perfectly safe. The live lead, it's nowadays brown, should have no stray strands. There should be no bare wire showing at all outside the junction box. Then, and only then, with the earth lead properly connected, is the fire safe to use. There's no chance that the casing will be live, as we can test by using the light bulb again. It's quite safe to touch. although of course it may be hot when it's been on for some time. Now a word or two about electrical plugs. These must be wired up correctly. Power cable has 3 separate leads. Earth's in the middle, neutral on the left, and live on the right. The live lead, nowadays coloured brown, goes to this terminal, which will have a letter L somewhere near it. The separate strands of wire must be twisted together and the whole looped neatly around the terminal. All screws must be firmly tightened. That's the live connection. The earth lead is nowadays green and yellow and connects to the top terminal, which will have an E near it. The neutral lead is nowadays blue and connects to the left-hand terminal, which will have an N somewhere near it. Like this, the plug wouldn't work. We've got to put in a fuse. Modern fuses consist of a wire of suitable thickness enclosed in a small cartridge. They're marked with the greatest current they can carry without blowing. This 3 ampere fuse is right for an appliance like a television set or hi-fi. A reading lamp would need a 2 ampere fuse. We need a fuse with a thicker wire for more powerful appliances. A 13 amp fuse is used for things like electric fires, convector heaters, irons and kettles. The fuse goes in like this, and then the top must be firmly screwed in place. You mustn't be able to see the separate leads inside the outer covering of the cable, and the whole thing must be firm and tight and fitted with the correct fuse. Houses should be wired up on the ring main system. There's got to be a joule meter to measure the amount of electricity used, and a fuse box and main switch for the ring main circuit. The cable, this is a mock-up of a power circuit for fires and so on with thick power cable, is installed in a great loop with sockets at various convenient places, in the skirting board or on the wall. In this layout, each socket has its own switch. You can see that it's laid out in a loop, the ring main circuit. If we look at the back, you can see how the 3 leads enter and leave the socket. For permanent wiring, the live lead is red, earth, here coloured green, and neutral, black. All home wiring should be properly connected up like this. There are many electrical gadgets in a kitchen. Electric kettles must be plugged into the power circuit with 13 amp fuses in the plugs. So must washing machines, which have high-power electric heaters in them. The fridge should have a plug with a 5 amp fuse. Electric cookers take a very large current when everything's switched on and must have their own quite separate power circuit with very thick supply cables. You can't wire them up yourself or run them off the ordinary ring main. Electric immersion heaters also run off quite separate circuits, and you can't install them yourselves. House lighting takes a relatively small current, and there's always a separate lighting circuit. Here, the fuse in the plug must be only 2 ampere, so it blows and cuts off the current if it becomes greater than that, because of a fault of some kind. Otherwise, the thinner cable of the lighting circuit might heat up and cause a fire. There should be a proper fuse box with a fuse for each ring main circuit and for each lighting circuit, as well as fuses in all the plugs attached to various appliances. Where the main supply comes into the house, there should be a main switch and company fuses which can only be replaced by electricians working for the electricity supply board. And of course, there's got to be a meter. As we said before, misusing electricity can be highly dangerous. The fire safety officer again.
A simple domestic appliance can be a source of hazard. Take this iron. The plug, what's left of the iron itself, and the wiring with the insulation stripped off. The lady who used this used it regularly, every day, to iron her daily washing. What she didn't realise that As she was ironing, the flex was rubbing on the edge of the ironing board, and after many weeks of this process going on, eventually the insulation wore through, the wires began to arc, and in fact caused a small fire which could in fact have been a lot more serious. This double adapter was taken from a house where the occupier had used not only this one, but a second one into the front, and then taken off additional appliances. These additional appliances, such as electric fires or kettles, caused too great a load on the system, and one can see where the pins had begun to overheat and melt and burn the plastic. This could have been the start of a very serious fire. Fuses must be correctly rated. In this particular house, the fuse box was the source of a fire. A short had occurred, and unfortunately, the occupier had fitted a non-standard fuse, in fact, a piece of copper wire. It obviously did not blow, and meant, therefore, that the insulation on the wires began to melt. When the wiring had been put in, it had been placed next to a gas pipe. And as the wiring got hotter and hotter, this in fact melted the gas pipe, making a small hole, allowed the gas to escape. The gas was ignited by the burning insulation, and a serious house fire occurred, creating severe damage to the ground floor of the dwelling.
You must understand the simple facts about electricity and never do things yourself which you don't understand. Mistakes can cause a lot of damage. Mistakes can kill. Mistakes can kill. In this film, we're going to look at some experiments which tell us something about a very important and interesting part of physics: radioactivity. First of all, a way of detecting radioactivity. This battery is connected to two metal plates with a gap between them. That's an insulating sleeve. And here's one of the plates. And this other lead's connected, again through an insulating sleeve, to the other. There's air, of course, between the two plates. One of the leads is connected also to this sensitive galvanometer. This shows no deflection, because the air between the two plates does not conduct electricity, and no current can flow. But suppose we place a sample of a radioactive substance under the plates. A current passes. The invisible radiation coming off from the source is making it possible for charge to pass across the gap between the plates. If we remove the radioactive source, current stops flowing. Replace it, and current flows again. Our radioactive source, it contains a radioactive element called Americium-241, is giving off charged particles called alpha particles, some of which are passing up between the plates and causing the effect we've seen. Now see what happens if we place an ordinary thin paper tissue over the radioactive source. It must stop the alpha particles, for the current falls to zero again, and then passes once more when we remove the tissue. Alpha particles are heavy particles which are very easily stopped in their tracks. This is a form of radiation which is not very penetrating. What causes the current to pass? Is it the alpha particles themselves, or is it the effect they have on the air between the plates? Here's a way of finding out. We've got the same radioactive source containing Americium-241 and the same arrangement of two plates, but this time we put them in a glass container from which we can pump out all the air. A metal gauze cover will shield us from flying glass if the vessel shatters when it's evacuated. We make the same connections as before. Current passes just as it did before. Will current still pass between the plates if we remove the air from between them? Let's use the vacuum pump to find out. Alpha particles are still streaming off from the radioactive source, but look, the current quickly dies away. Without air present, the radiation does not cause the current to flow. No air, no current. The alpha particles, the radiation, cause a current to flow because they affect the air between the plates, producing charged ions which carry the current. Let the air in again, and a current passes once more. Cutting off a block of solid carbon dioxide to use in a diffusion cloud chamber. This is a device which enables us to see radiation, such as the alpha particles whose effects we watched in the last experiment. Contact with a warmer metal plate causes these strange sounds. We pour on alcohol. A plate with a felt pad on top. More alcohol to soak the pad. A glass cylinder. A lid with another alcohol-soaked pad on its underside. Inside this vessel, we're going to mount a rod which has some radioactive radium-224 at its tip, another source of alpha radiation. Don't worry about the purpose of these electrical connections at the moment. You can find out about them afterwards. A lamp is now switched on. Inside the glass chamber, it gets colder and colder as one passes from top to bottom because of the solid carbon dioxide underneath. Alcohol vapor sinks slowly downwards from the pad under the lid. The tiny invisible alpha particles streaming off from the needle hit some of the molecules in the chamber and turn them into charged ions. Alcohol condenses, forms liquid droplets on these ions, and so reveals the paths of the alpha particles. We're looking at the tracks of alpha particles shooting off at random in all directions from the radium source. The tracks sink downwards because the liquid droplets fall under gravity. Watch. This is radioactivity in action. For a third experiment, we're going to examine an important feature of radioactive substances. Their radioactivity gradually falls, decays, as time passes. We shall measure one particular radioactive decay. This is a counter, a measuring device based on the same principle we met at the start of the film. Radioactive particles cause a gas inside to become electrically conducting. Each particle causes a click. At the moment, it's measuring background radiation, the natural radiation that's always present from the various materials around us and from cosmic rays. This apparatus will count for us the number of clicks in 1 minute. The number shows up at the top left, there. Coming up to 1 minute. Background count, 14 counts in 1 minute. You can take readings down as the experiment proceeds. This is a neutron source, which we're using to create a radioactive element. The element indium, in the form of a metal foil, has been placed inside. Now, after several hours, it contains a radioactive isotope of indium, which gives off charged particles called beta particles, lighter than alpha particles. Listen. We shall shield the counter from all background radiation using these lead blocks. Then measure the radiation every 15 minutes as the indium decays. We start at 9 o'clock. If you want to do the experiment, make a note of this time. Now let's see how many counts there are in 1 minute. How many beta particles are given off? Here it is, 556 counts per minute. (9:15), 15 minutes later. Now 478 counts per minute. The radiation is decaying. 9:30. (363 counts per minute. 9:45. (297 beta particles per minute. 10 o'clock. (263). 10:15. There are now only 233 counts in a minute. 10:30. (171 counts. 10:45. 140. 11 o'clock. The counts have now dropped to 130 per minute. "15 minutes later. (11:30). Down to 96. Last time but one, 11:45. Only 77 counts. Last reading at 12 o'clock. "62 counts per minute. You can afterwards draw a graph using these readings to show how the radioactivity decays. You plot counts per minute on the vertical axis and time in hours on the horizontal axis. There are the points. And this is what's called the decay curve. All radioactive elements have this kind of decay curve. It's called an exponential curve, although some decay much more slowly than others. The background count we measured is shown by the dotted line, and you can see that the radioactivity of the sample is approaching the background value after only a few hours. This was a short-lived isotope. This is an experimental nuclear reactor at the Harwell Laboratories of the United Kingdom Atomic Energy Authority. One of its uses is to carry out all sorts of tests on the effect of radiation on various materials for the nuclear industry. Inside a reactor, this is a cutaway model, there are fuel elements arranged in such a way that nuclear reactions take place which generate heat. There's also a great deal of radioactivity inside the reactor, so there has to be a lot of shielding around it. There's a 4-inch thickness of lead to stop gamma radiation, and a 6-foot thickness of concrete around that to stop the particles called neutrons from getting out. Here's one of the cans containing nuclear fuel for the reactor, uranium in this case. It's quite safe to handle before it's been used in the reactor, but when it's removed, because the nuclear fuel has been used up, it's a very different matter. They're removing a spent fuel element. It's so dangerously radioactive that it needs this huge container, it looks like a space rocket, to carry it in. This weighs 21 tons and has thick lead and steel shielding, all to carry one of those quite small fuel cans. The very radioactive spent fuel element is taken to a special building where it's going to be stored for a year or so while the radiation decays. It's going to be dropped out through that small circular hole. Into a deep tank of water. There it goes. This depth of water shields the workers above from the gamma radiation. Gamma rays are like X-rays, only they have shorter wavelength and are even more penetrating. Now the ends of the can are sawn off, all by remote control, underwater, leaving the center portion which contains the radioactive spent fuel. The can is now passed through to the storage pond, where it will remain until its radioactivity has greatly decayed and it's no longer so dangerous. Here it comes. It's going to be kept upright at the bottom. All these precautions show one of the difficulties about using nuclear reactors. The waste produced can't just be dumped. It's got to be looked after very carefully, although it can eventually be reprocessed to be used again in the nuclear industry. The invisible gamma rays coming off from all these decaying spent fuel elements are highly dangerous to living things. In fact, the radiation at the bottom of the pond would be absolutely fatal if we were exposed to it. This gives us a use for this decaying nuclear waste. These drums contain surgical instruments which need to be sterilized. They're things like plastic disposable syringes, for example, which would be damaged by heat treatment. They're sealed in plastic bags, then placed in the drums and lowered into the pond. Once the drum's near the spent fuel elements, it's exposed to intense gamma radiation. This kills any bacteria present, so that the instruments become absolutely sterile and can be safely stored inside their plastic bags until they're needed. They mustn't be left too long, however, or the radiation would damage the material the instruments are made of. Gamma radiation can harm plastic. After about 24 hours, the drum is taken out. The contents don't themselves become radioactive, and this is a very good use for gamma radiation. The fact that the label on the drum has turned red, it was yellow, indicates that the drums have had just the right amount of radiation. Radiation can be a dangerous thing. It's important that everyone should understand enough about the subject to be able to judge when it's being used to our advantage and when it might become our enemy. Heated metals expand. Cooled metals contract. In this film, we'll look at some of the consequences of the expansion of metals. Physics in action in the world around us. First, a demonstration in the laboratory. We hang this piece of metal from a metal wire stretched between two supports. Now we pass a current through the wire. This causes it to heat up, and the wire expands. It gets longer and begins to sag. Increase the current further, the wire begins to glow red hot and sags still further as it expands. Turn the current off. The wire cools and contracts again, back to its former length. Current on again. It's expanding once more.